Okay, in experiment 1, and we'll be performing experiment 1 and 2 during the first 2 weeks of the semester. Half of you will do experiment 1 in week 1 and half of you will do experiment 2 in week 2 and vice versa. But there's two ways to characterize organic compounds, two types of physical properties that we can use to identify basically the identity of unknown compounds, and one is melting points and the other is boiling points. So in experiment 1, what you're going to do is you're going to measure the melting points, learn how to measure melting points of organic molecules, and then do a mixed melting point, use the mixed melting point technique in order to basically determine the identity of an unknown solid. So in general chemistry, you learned that the melting point is the temperature at which the solid and liquid phases are in equilibrium. I mean, it's more easy to just remember that, when a solid melts or when a liquid freezes, that's the melting or the freezing point, which are exactly the same temperature. So in organic chemistry, we can use the melting point as a physical property to help identify and determine the purity of a solid. Basically, if there are over 9 million organic molecules, X number of those are solids, and if we have the melting point of a solid, that might exclude 5 or 6 million of those compounds, probably a lot more. But the melting point alone can be used either to narrow down the possible list of unknowns, or sometimes in forensics the melting point will tell you clearly that that material isn't what you're looking for. If you had a white solid of, let's say, some illegal drug that melted at 50 degrees and your sample melted at 100, then you could clearly say, well, that's not that sample. So what we're going to do is first learn how to take melting points of organic molecules, and every time you make a solid in the lab course, you're going to measure its melting point and compare it to the literature value that you can find in places like the Sigma Aldrich website or the CRC handbook or any list of literature values. So the apparatus that we use is called a melting point apparatus. There's two types that we have in lab. One is called a Meltemp, and the other is actually from the Vernier company, and they both operate the same way. Basically what you're going to do is place a small amount of solid into a very thin melting point capillary. You're going to place that inside of a heating block that's going to heat at a certain number of degrees per minute. You have a thermometer there to measure the temperature, and what's going to happen is at some point the sample is going to melt. You're going to observe that, usually through a magnifying glass, and then then you can determine the temperature or the melting point of the sample. It doesn't take much to get a melting point, usually just 1 to 2 millimeters of the solid is placed in this really thin, what we call melting point capillary tube. So the procedure for making the melting point is simply to take the melting point capillary, which is open on one end and closed on the other. You place a small amount of the solid on a watch glass, and then you tap the capillary tube onto the solid until you get a certain amount of that into the capillary. And then we in lab we can pack the solid down to the bottom of the tube. Remember, it starts out up here at the open end of the tube. To get the solid down into the closed end of the tube, you can either just simply tap it on the bench top, or you can use what's called the bounce tube, where we just simply have a glass tube. You put the sample in, it'll come down and bounce a couple of times back and forth, and that will pack the solid down into the capillary tube. Now ideally we want 1 to 2 millimeters of sample here, or just a small enough amount that we can see. Just in order to get a good picture, this is definitely more than 1 or 2 millimeters of the solid. So we put the sample into the capillary tube, we pack it down to the bottom of the closed end, and then we place it inside of the melting point apparatus. where we're going to measure the temperature and we're going to heat the sample. We have most of the apparatus in the lab are these melt temps. We do have a couple of the newer vernier ones, and both have slots where you can stick a capillary tube. You can actually stick, in some cases, up to 3 capillary tubes in the melt temps. And over here you can clearly see that there's 3 slots to put in the melting point capillary into the vernier system. So we place the solid in there, and then we heat the sample at a very slow rate, usually 1 to 2 degrees Celsius. And ideally then, as the sample heats, as the block is heated, the sample's heated, so that we're measuring the temperature of the block, and when the sample melts, we'll be able to measure the melting point of the sample. Now, I should step back here for a minute and just talk about the differences between these two apparatus in terms of the heating, and also, do you really have to heat between 1 to 2 degrees Celsius per minute? This slide should say per minute. If you know the literature melting point of your sample is something like 130 degrees, typically what we'll do is heat the block rapidly up to 120 degrees, and then as we pass through the melting point, we want to go at 1 to 2 degrees Celsius per minute. And so we don't have to heat the entire time at this slow rate, just where we go through the melting point of the sample. And most of the time, we have a general idea as to what our literature value is. So if nothing else, we can get within 20 degrees of the sample. On the melt temps, there is no temperature. There's no temperature on the knob. It basically is just the amount of heating, with a 0 being no heating and 10 being maximum heating. So you kind of have to go trial and error as you adjust the knob to get the heating to the proper temperature. The verniers are actually a little bit easier, and if you were to use this one, you would see that the temperatures, there's actually a maximum temperature that's on the dial. So if you basically have something that melts at 150 and you put the knob at maybe like 160 degrees, it'll go through the appropriate heating rate to get you to 160 degrees. But there's only 2 of these, and there's another 15 of these, so you're going to be using the melt temps for the most part. But the idea is get close and then go slowly through the melting point of the sample, and it'll be clear in a few minutes why that's the case. So here's what happens when you measure the melting point of organic solid. First of all, in general chemistry, we're used to melting points and boiling points being a single number. That's not the case in organic chemistry. Melting points are typically a range. And the range that we use is that the first number in the range is where the sample just starts to melt, or there's a physical change in the sample. So what we do is the sample may look like this before it starts to heat. After you heat it, at some point you'll see some physical change happen to the solid. Maybe it'll start to melt and you'll see droplets. Sometimes it sweats. That's what sweating is called. You can sometimes see it expand, but there's some physical change. That's the first number in your melting point range. And then the second number comes after all of the sample is completely melted. And so your range of organic melting points will be from where it first starts to change physical appearance to when it's completely melted. And this range can be very important in terms of determining the purity of the sample. Now, the first thing we can do if we're looking at the purity or making an identification is we can look at the literature temperature, and we can look at our melting point temperature of our unknown. So the literature melting point might be 53 to 54 degrees, and we get a 52 to 53 degree measurement. We're pretty close. So the first test of purity is how close you are to the literature value in terms of the temperature. The second is the actual size of the range. The width of the range and temperature is also an important part of measuring purity, because if you've got a range of, let's say, 10 degrees Celsius, it means the sample is very impure. 1 to 2 degrees is typically what we find. So ideally then we have to choose our conditions to try and get the most accurate melting point in the smallest possible range. So it's important that we heat at a slow rate, 1 to 2 degrees Celsius per minute, and it's also important to use the smallest amount of solid possible. You might say, well, why is that? We want to use a slow rate of heating, because if you think about this aluminum block, it's going to be heating at 1 to 2 degrees Celsius per minute. If the block is heated very quickly, there'll be a time lag between the sample starting to melt and finally completely melting. Well, the block is going to go up a certain number of degrees during that time frame that's going to artificially raise the range of the melting point. And so what we'd like to do is go very slow, so that ideally all the thermal energy in the aluminum block is being transferred to the sample, but that the aluminum block doesn't change its temperature very much during the course of the time period that it takes to melt the sample. And so if we go very slow, we'll get what should be the most accurate representation of the range. If we use a small amount of solid, then there won't be that lag time between the sample starting to melt and it completely melting. If we use a lot of solid, then there's going to be that lag time between the sample starting to melt and completely melting, remembering that the block is going to go up in temperature during that time frame. So we want to go as slow as possible and use as small amount of material as possible, simply so that the block doesn't artificially appear to be higher in temperature, and that'll raise the range of the melting points. Okay. Now, impurities in the organic material depress the melting point, so we get what's called melting point depression. Now, if you go back to general chemistry and remember that melting a solid into a liquid is the opposite physical property of freezing a liquid into a solid, then the freezing or the melting point are exactly the same. And in general chemistry, you learned about the freezing point depression equation, where the delta T sub F equals K sub F times molal concentration. So delta T is the freezing point depression in degrees Celsius, Kf is the freezing point depression constant, and we in general chemistry measure the concentration in molals, and remember that a molal is a mole per kilogram of solvent. So we will always get, for an impure sample, a melting point that is lower than the literature value. Okay, that's just this equation. There's no other way around it. And the other thing is that K sub F, when you were in general chemistry, the K sub F is pretty small. If my memory's right, it's like 1 degree Celsius per molal. It's a very, very small number. But for organic molecules, the K sub F can be incredibly large. K sub F is about 20 degrees per Celsius in some organic solids. And in general chemistry, if you measured, I think you used lauric acid if you had faith, the K sub F is huge, so you get very large temperature. You get very large temperature changes given very small concentrations of material. So in the previous slide, where they said that a 1% impurity can cause a half a degree depression in the melting point, they're taking an average K sub F value and then sort of using a 1% molal impurity. So the idea here is that if you do have impurities in your sample, you'll get a depressed melting point, and you'll also get a fairly large range, 6 to 7 or 6 to 10 degrees Celsius, as opposed to the 1 to 2 degrees Celsius range, and a range that's very close to the literature value if your sample's pure. So we use melting point as a qualitative test of purity. It's not perfect, but it's good enough for what we do during the course of the year. Okay, so you get melting point depression from the impurities. Now, what we're going to do in this experiment is you're going to be given a solid unknown and a list of possibilities for that, and you're going to identify the unknown based on melting point. Now, can melting point be used as a physical property to determine the identity of the unknown compound? Yes and no. If you had two compounds that have very different melting points, and the caveat here is they're measured in the same instrument using the same conditions, then you can assume they're not identical. This is used maybe a lot in forensic chemistry. If you had a white solid, and you wanted to know if it was an illicit drug, you might take the melting point of it, and it might rule out 9 out of 10 illicit drugs. On the other hand, if two compounds have the same melting point, are they absolutely identical? You can't determine that from melting point, because if there's 9 million organic molecules, there might be 5 or 6 of those that have the same melting point or have the melting points within a couple of degrees of each other. So to make an authentication or to make a determination, what you end up doing is you end up doing what's called mixed melting points. And so what you do here is you take the unknown sample and you mix it with a small portion of the known material. And then you measure the melting point of that mixed sample. In this experiment, we're going to mix 2 parts to 1 part, 2 parts of unknown solid to 1 part of a known authentic, and see what the melting point of that mixture is. And so we can ask ourselves the questions, and if you want to see if you understand what's going on, stop the tape and see if you can answer these 4 questions. Okay, if you didn't stop the tape, then let's go over them. So what happens to the mixed melting point if the known and the unknown are the same compound? If they're the same compound, your mixed melting point temperature range, the absolute value, like 53 to 54 degrees, should be the same as what you measured for the unknown. The range shouldn't change. On the other hand, what would happen to the melting point of the mixture if the unknown, or the melting point range, will be exactly the same? What happens to the melting point if the unknown and the known are different compounds? Well, now the known is going to act as an impurity, so you're going to get a lower melting point. And you're going to get what for the range? You're going to get a higher range. So the idea here is if you make the mixed sample, it should have exactly the same melting point and range as the unknown sample if they're identical. If they're not identical, you'll get melting point depression and a big range. So it's easy to tell if the 2 compounds are the same by doing a mixed melting point. Okay. So what we're going to do in this experiment is, the first thing you need to do is learn how to measure a melting point. And you're going to be measuring melting points over the course of the year. So you're going to start by determining the melting point of the lowest melting authentic sample that's in the chart in your handout, and that happens to be 2-acetonaphthone. I realize this is the first 2 weeks of class. We haven't talked about naming organic molecules, so this might as well be called compound A, but it's a compound called 2-acetonaphthone. You're going to take that sample and you're going to practice your technique and also compare the melting point that you get for this versus the literature value, and that'll give you some idea of how well the melting point apparatus is calibrated. If it's not calibrated well, there's not a whole lot we can do about that in this experiment. If you get a melting point that's 5 degrees below the literature value, just keep that in mind when you're given your unknown, that your unknown probably has a melting point 5 degrees higher. What you're going to do for each sample is, for the 2-acetonaphthone, is you're going to make two separate capillary tubes full of samples, and you're going to measure the melting points of those 2 independent samples. We never determine the melting point on a sample in a capillary tube, let it freeze, and then remeasure its melting point. Okay, we never do that. Why not? Because if the sample decomposes while it's melting, you're going to get impurities, and so when you measure the second melting point on the same sample, basically you're going to get a lower melting point. Hey, that might be a great test to see if the sample decomposes when you melt it, but that's not what we're after here. We're after the most accurate melting point we can get. So we always do melting points on two different samples. If the two samples are similar in melting point and range, then you're fine. If not, do a third. Okay, so that's the first thing. Learn how to make the measurement and measure it on the lowest melting point sample so that you can basically calibrate the instrument. You might say, can I use any sample? Sure. If you want to measure your melting point, practice melting on something that melts at 150 degrees, and then you get an unknown that melts at 50 degrees, you're going to have to wait for the instrument to cool. So that's why we choose the lowest melting point of all the standards. Okay. Then you're going to be given an unknown in a test tube. First thing you do is record its number in your notebook. Okay, if we don't know what the number of the unknown is, we can't grade it. If we can't grade it, you can't get a score. So you record the number of the unknown, then you measure the melting point of the unknown, again using two different samples. If they're close, that's okay. If they're not, do a third. And then what you do is, using the center of the melting point range, you're going to make a list of potential compounds by using a range that's plus or minus 7, and you're going to use the chart, and this is the chart from the handout. So let's say I measured the melting point of a solid, and I got that it had 126 to 127 degree Celsius range. That was the melting point of my unknown. So what I'm going to do is, I'm going to basically go from about 126 degrees, I'm going to go up 7 degrees, and I'm going to go down 7 degrees. So if I go down 7 degrees, that would probably take me to there. So here is my list of potential unknowns. And you can see that there's kind of a break point between 133 and 140, and a huge break point between 56 and then 120. So here's my possible unknowns. 2-naphthol, transtilbene, orthobenzoyl benzoic acid, furoic acid, and benzoin. Okay, those are my possible unknowns. Okay, so that's how we determine the possible unknowns. Now what I'm going to do is I'm going to prepare mixed melting point samples of each of these solids. Okay, and so I'm going to then prepare these in a 2-to-1 ratio of unknown to known. I'm just going to estimate those, basically put two little piles of solids on the watch glasses, blend them together, pack them in the melting point capillary, and make the measurement. What should happen? Well, if the melting point and the melting point range of the mixed sample are considerably lower and the range increases, that's not the right one. And so, in some cases, if it's dramatically different, you only have to do one melting point sample. You don't have to do 2 replicate trials. Now, of these unknowns, of these possible unknowns, one of these is going to give exactly the same temperature and range as the unknown. Exactly one of those mixtures is going to match. The rest of them should give a depressed melting point and a large range. Now, if you just so happen to have the first sample that you do have exactly the same temperature of the mixed sample and of the unknown, does that mean you only have to do one sample? Absolutely not. You've got to do all of the possibilities, all the possible unknowns, to verify that indeed you have one that stayed the same and the rest depressed their melting point. So you just can't do one. Okay? If you do, you'll see a huge deduction in your lab report. So you've got to do all of the possibilities. Okay? So then from those results, you should be able to determine the identity of the unknown. The report that you're going to fill out for this is you're going to fill out a report form that's included in the handout and is available on the Blackboard website. You can fill that report in by hand, or you can type it up, it doesn't matter. But for this experiment, there's going to be no electronic copy that you need to turn in. So if you want to print it out, you can just hand write it. Now, during the experiment, all the data goes in your notebook. So you're not filling out the form as your notebook, but you can fill it out later on by hand for this experiment if you desire. Okay, so at the end, you should know conclusively what your unknown was, and you will have learned how to measure the melting point of an organic sample. At the end of the experiment, you're going to dispose of any of your extra solids in a solid waste container that will be in one of the hoods in the lab. You'll dispose of all the melting point capillaries in a glass waste container, and then you're going to clean the watch glass with a little water and acetone, return it to an appropriate container, and then put your melting point apparatus back in the box, make sure that it's powered off, and make sure that the thermometer is powered off, and then put that box back in the appropriate area of the lab. And so at that point you will have finished experiment number 1.